Hello fellow neuroimagers. Today we are going to talk about 05 Lab. So we're just going to jump right into it. I've already actually written the code that we need for this one, so I'll just talk through it and hopefully give you a little bit of insight on anything that you may have tripped up on. So you can see all the output files already exist. So let's open up Jupyter Notebook. Navigate to Lab 05. You see all the files here. Here's the Python notebook that we used. And important, we run the top line as always, so want to be able to show images from Python in line if we do that, but I don't think we really do that for this lab. Okay, so the first problem, what if we did slice time correction first? That's the main idea. So the very first command is to use the slice timer command, which is our slice timing correction command, and we are just going to use it for our raw bold. So bold that just came off the scanner, and all we did was transfer it to our nifty format. We use that as input, so we copied that over from the first lab, and that is my underscore bold. Then we specify the TR, which is just 2 seconds, so time of repetition, 2 seconds. Then the output is going to be my bold underscore slice time, so just slice time corrected is essentially what that's going to stand for. And then the next command that we write is the FSL motion outliers. So again, we're just following the same steps as we walked through the lab, just we're doing slice time correction first. So now with the input of determining the outliers, we are now going to pass in the slice time corrected image, and the output is going to be the slice time corrected motion corrected image. And we are going to, well, I guess for this one, we aren't actually calculating the, or we're not actually outputting the nifty file that's motion corrected. We're just collecting the parameters. So so we're just using the frame-wise displacement metric to calculate the motion outliers, and we are going to pass out the time series into this file here, and then we can also plot it there. So this will plot the frame-wise displacement. So now we can compare the frame-wise displacement from the raw func, so that's the one that we didn't have any, haven't had any processing applied to it, versus the slice time corrected functional image. So we just look at the described files here, or the method that we use with pandas. So we use Python code from pandas to read the table in. So read table just meaning the text files that we created from the previous command. And using this, our FD, as a pandas table, we can use the describe method to give us some useful information about it. And the display here means that that the output from this command will display on the output file of the Jupyter Notebook, and this one will display in the Jupyter Notebook. Because otherwise, if I didn't have it, only one would appear. So to prove that to you, I don't think there's any preconditions to this cell that I also need to fill out. I think all the text files exist. So if I don't have the display commands in here, I won't see both of those as my hypothesis. So again, yep, so we don't see the raw FD one, we just see the slice time corrected FD table. So I'll hit Control Z to get those back and run this again. And now you can see this is from the raw functional, meaning that we haven't applied any processing to it. Let's see that the mean FD is 0.1. But when we look at it from the slice time corrected image, it's a little bit lower. Okay. And then this makes sense because when we apply slice time correction, there's a little bit of interpolation that occurs, and so the edges of the image may not be quite as sharp as before, meaning that they're going to be a little bit blurred, and that is going to maybe mask the motion that is occurring in the subject as they're going across the scan in time. So we see a little bit lower of a mean frame-wise displacement here. So now we're actually going to do the motion correction with McFlirt, and the input is going to be our slice time corrected bold, and our output is going to be, we're going to call it slice time corrected underscore motion corrected, so that's reflecting the order. And recall in lab that we did just the reverse of that, so we did motion correction then slice time correction. So yeah, the cost function, normal correlation ratio, the reference volume, this is the exact middle of the image that we're using. You can use Linux tools to also calculate this, or Python tools to calculate this, instead of hard coding it right there. Mats, those create all the .mat files that we will see, and the dash plots creates the .par files that you'll see. And we can see here that we are then we display the relative motion, the absolute motion, and we are looking as the interpolation step between volumes is spline. There's also nearest neighbor or sync. These are just different interpolation methods that we can use for motion correction. Yeah, we won't get into the mathematical details of those. So if we do the FSL TS plot command, we can make several plots with the files that came out of this McFlirt command. So if I double click on this cell, so this is one gotcha that several people ran into. These are markdown cells. These aren't Bash, these aren't Python, these are markdown cells. So markdown is its own kind of text formatting language where it has like special syntax to do certain things, such as inserting an image. So again, with inserting image, we start out with the exclamation mark. You kind of name the image. This can be named anything. We just call it wrote underscore image. And then in the parentheses, we actually display the name of the file that we want to display. And shift enter to run. And again, we can see here are the motion, the rotational components of the motion. So we can see rotation in the X plane, the Y plane, and the Z plane, or around these axes, I should say, around the X axis, around the Y axis, and around the Z axis. And we can do the same thing for translations. So this is more like what I said before, with movement along the X plane, movement along the Y plane, and movement along the Z plane in our images. And then finally, we can calculate just total displacement. So if we combine the translations and the rotations to come up with a metric of what's the total Euclidean distance that was moved, or like the total distance that was moved for either for the relative, meaning from previous volume to the current volume, or absolute, which is in reference to a center volume, which should be about 157 right here. And yeah, we can see that for the relative motion, we don't see a lot of rapid shifts until the very end. And for absolute motion, yeah, again, we see a slow trend towards the middle because this is where our reference volume was, and then we see they go up again because it's falling farther away from the center reference volume. And again, even in the absolute motion, we can also see a little blip at the end there. So now we can run motion outliers on the two orders of the files that we saw. So again, we see it with slice time correction first, then motion correction. And then with this one, it is motion correction first, then slice time correction. So the first thing that should pop out is just the scaling of the y-axes between the two. So we see when we do slice time correction first, the overall peak of the motion is much reduced. So if we did motion correction first, then slice timing, we see that we have a peak of around like 0.27 millimeters at the end here, but we have taken off an entire tenth of a millimeter here. And we can also see across time, these are just a little bit sharper looking, right? So we can kind of tell, well, this one is a good example right around the 240 mark. So we see it comes to a very sharp peak and then goes back down. Whereas for when we do slice time correction first, we see a little bit of a thicker peak up here. And this could be due to the interpolation that I was talking about before, where the slice time correction can kind of blur the edges of the brain a little bit, causing some inaccuracies and just some inaccuracies in the motion estimates. And again, we can use the pandas to read in the text files for our FD measure, and we can compare the two. So there isn't a lot of difference between the two except for the max that I pointed out here, and even still with that max, doing motion correction first has, I guess, probably near negligible decrease in overall frame-wise displacement. So the benefits of doing motion correction first or slice time correction first may not pan out so much in seeing changes in FD. All right, I think that is everything that I wanted to cover. Yeah, and I think that'll put you all on the way to be able to answer the questions. And if you have any questions about the code, you always know where to reach out on Slack. And that will be all for today. Thank you so much for listening. Bye-bye.